Hello everyone, good afternoon. Welcome to Efficienergi's webinar series. Today's topic is protective device coordination in data centers. So Q&A is open for all. If you have any questions in your mind, you can drop there and we will take that in later in the session. We will run live polls during the session as well. So please stay engaged. So we will begin with the session. So today with us, we have two industry experts as a panelist who will guide us through the session. First, Mr. Rajen Mehta, and then Mr. Prasad Gore. So, Mr. Rajan Mehta, he is a CEO of Efficienergi Consulting Private Limited. He comes with 24 years plus of experience in power quality, reliability, and electrical optimizations. He is a postgraduate and chartered electrical engineer. Also, he is part of national standard building committees like BIS and IEC, and he has contributed to numerous standards. For example, IS 17036. So Mr. Rajan Mehta has worked with 2 megawatt to 150 megawatt DC projects across India and in the US throughout the project life cycle of a data center, whether be it a greenfield stage, operational or expansion. He has led 200 plus advanced power system studies, voltage stability, harmonics, power quality, all across the India, and also executed testing and commissioning for more than 300 megawatt of greenfield data centers. And he is an expert in L1 to L5 complete MEP services. So I will just ask Mr. Rajan Mehta to take the stage.
Hi, good afternoon, everyone. First of all, very gratitude for joining in the midst of Tuesday afternoon for this interesting topic. Uh, and thanks, Nikhil, for the introduction. Um, I will introduce my co-panelist. Very happy to have him with me, Prasad Gore. Um, we were together many years ago, and we have come back together on this very interesting journey for ensuring reliability and safety in data centers. So, Prasad, to give you a very small brief, also brings more than 20 years of experience in power systems. Has had a wide range of stints, right from my initial journey when I was in my first avatar in my first company. We were together, commissioning power conditioning systems and doing a lot of R&D, developing thyristor-based switching devices and all that. And from that, his journey took off. He has had a successful entrepreneurial stint as well. And his last 10 years has gone into deep diving into power systems, power system coordination studies, load flow studies, arc test studies, and so on. So very glad to have him on board along with our team. And what we have planned for today, which is going to be the first in a series of quite a few webinars in this topic. Because while we were planning for this, series, we realized that protective device coordination in not only data centers, it's applicable for any mission critical industries, right? And that is something which is has both a science and art combined, and it has many nuances to it with respect to how the perception of the customer whose facility it is. Are they looking for a more reliable and a more stronger system, or they're looking for more safer system and so on? So there are many perspectives which come across when you're trying to do a protective device coordination study. And hence, what we realize is that before we dive directly into how to how to do a coordination study, or what kind of challenges do industries face, typically practical case studies, we thought we need to go back to the basics first before we actually showcase you in the next few series on actual case studies that we have been working in across more than almost 1 gigawatt of capacity of data centers across the world. So that experience is what we thought will bring out, to with our fellow practitioners, fellow experts, industry experts, end users, clients who have been fortunate to join us, and we have a great attendance today. So let's get cracking. So today what we'll focus on is primarily protection devices. That will be the core, I would say, topic of today's webinar: tripping characteristics of protection devices. So we are starting off this as a part one, and probably this will be a five-part series webinar that we are planning to roll out. So here our first job today will be to deep dive inside what constitutes the different nuances of protection devices, so that once we have a good understanding of those, that will allow us to build upon as a foundation to doing a better protective device coordination studies. Right. So having said that, we in protection devices we have three primarily devices that we are going to be talking about: fuses, low voltage circuit breakers, and relays, protection relays, as we call them. So these are the three elements which are in a way the core, the entire protective device coordination studies revolve around these three PDs, as we will call them throughout the webinar, for protection devices. So these PDs, we will be deep diving inside these PDs. What goes in terms of differences between these, what goes in terms of nuances to allow us to do a better coordination study. Those are the things that we'll be deep diving into. A question may arise that why do we talk about the fuse? But that is also as much important, which we'll see in some examples that we'll take. So before we dive, just to test the audience's knowledge and us to understand where does our audience sit, right, in terms of their understanding, to better tune the content. There'll be a poll right now on your screen, which will encourage you to please answer. As you can see on your screen, the poll is about what. Can you go to the next slide? Yeah. What does GG mean on a fuse? If at all amongst you people have looked in a little magnified view on a fuse, and which you see on the screen also in the presentation, there is a short acronym, not an acronym, an abbreviation of small g and a capitalized G written on the fuse. What does that constitute? If you can please answer, that will be great for us to have an idea. So we have still very few votes coming in. We would request more people to please be active. About 30% of participants have voted. It's 35. All right, interesting results. Does tell us that there is a lot of education required on the side of participants. Okay, we have about 50% of results out there. Okay, and from the audience side, if we were to conclude the poll, uh, so we can conclude the poll. Yeah, we can publish the result. So if you see the result, 51% of participants have voted for this as a general purpose fuse, whereas 23% said it's denoting full range braking capacity, and 23% said all of the above. So I think at this point, I'll introduce Prasad and let Prasad take over to give you the true result and why is that so. We are pleasantly surprised at this to understand the result. Yes, Prasad, please.
Yeah, thank you, Rajan sir and Nikhil, for introduction and giving me this platform to share the knowledge that I have. So, as we have seen the poll, so I am just sharing my screen. So I'm just sharing my screen. Just for us. Okay. Now the answer is basically all of the above, because the first G is basically stands for full range braking capacity. The first small letter only denotes for the braking capacity of the fuse.
And the second one is the bigger one, is the purpose of the fuse. So general purpose fuse, that is the correct answer. Again, this GG we can use in the motor protection as well. So the option, all of the options were correct. There is also one small letter which is, we rarely see this A. So this is partially range braking capacity. So this braking capacity and everything that we will be covering in our next webinar, which is on the short circuit. So presently, as we have started with this webinar on particularly talking about the tripping characteristics. So we'll move on to the next slide. So basically, this is what is TCC. TCC means time current characteristics. So here, here you can see this is a very typical TCC that you all must have come across. But then this is the definition. It is a graphical presentation, shows the set of coordinates of energizing quantity. Here we are talking about the current. So example is the current, because energizing quantity can be anything. It can be current, it can be voltage, or it can be any auxiliary binary input to the system, versus operating time obtained by specified curve equations and actual testing of the protection devices. So this TCC, we'll be talking more about it as we go on the further slides. So presently, this is the definition. This may not be the definition that you might be finding in IEEE standards or IEC standards. So this is very general definition of TCC. Okay, now we'll be talking about the fuse. As sir said, why we are talking much about fuse, because in data center we rarely see the fuse is in place for the protection of the feeder systems. So fuse is basically for the protection of immediate protection of the transformers or immediate protection of the motors. So there we use fuses. Again, that topic that we'll covering in the other webinars, where we will be talking about the selectivity and protection. So here we are talking about the operating characteristics of the fuses. So it is comprising of basically two times. One is melting time, and the second is arcing time. And both these two comprising the total clearing time, that what we call it as a complete operating time of the protection devices. So here it is fuse. So then there is a further one more important aspect of TCC is tolerances. So here in fuse we can have plus minus 15% of tolerances. Again, the plus minus 15% in melting and plus 15% in clearing. Here tolerances we are having a separate slide. So in that particular section I'll be explaining more detail about it. So we know that it is again a pre-arcing time, which is also called as a melting time. So what does exactly does this mean is when there is a fault current goes beyond the fusing current, then obviously the fusing element will melt, and then there is an initiation of arc. So this time basically starts from the fault current and ends at the where the arc is initiated, that the fusing element completely melts down. Then comes the arcing time. Arcing time is again the initiation of arc and complete extinction of arc. So the time between these two is called arcing time. So these two both add up together gives the total operating time, which is actually the complete fault clearing time of the fuse. Okay, now the IEC standards want every fuse manufacturer to be in line with their standard specified conditions. So for that, every manufacturer needs to give them the proper TCC for particular series of the fuses. So for that, particular test has to be carried out, and this diagram will show you the particular test that has been carried out. There is one circuit made for injecting a short circuit current. This is also having a particular X by R, because you are familiar with the short circuit rating. that is completely based on what power factor, what short circuit power factor we consider for the short circuit test, that has to be specified. So this particular test bench is arranged. Then there is a fuse element where we want to create the TCC for. Across this, one voltage measurement in terms of waveforms, that is oscilloscope, is connected. And let's say this is the proper, because again, this waveform will have a specified condition that it will not have harmonics. This is a pure sinusoidal waveform that is created by some source here. And then the fault is created, and this you can see the fault current, it starts. So initially across the fuse, there will be no voltage because it is in series. So a small voltage will be seen, which is voltage drop across the resistance of the fuse. Then what happens at this moment, you can see the voltage is rising and the current is reducing. So this point is where the fusing element has melted down and the arcing current has actually started. So arcing current will always be lesser than the fault current, and there will be a voltage rise. So from this to this, we measure it as a arcing time. And after the complete extension of arc here, there is a sudden rise in the voltage across the fuse because the fuse gets open. And this is what we call it as a TRV, transient recovery voltage. Again, the TRV is a very important topic that we'll be covering in short circuit webinar. So here, this particular time will be the melting time. This time will be arcing time. And this complete period is the operating time of the fuses. So also now you might not have seen this test and the diagrams, but this is a very regular diagram that we see for arcing time and operating time of the fuse. So this is basically the prospective fault current, and we basically use the current limiting fuses, which starts melting at very lower value than the prospective peak. So this is what we say the lead through peak of the fuse. This gives the current limiting features of the this represents the current limiting feature of the fuse. Here the first part we say this is a melting time, and then this part is basically we say arcing time. So A plus B comes out to be the complete operating time of the fuses. So we have explain you what is the test that is to be carried out to determine the operating time of the fuses. And on the similar ground, the test has been done for all the protecting devices. We'll have a different test setup, but the concept behind testing and producing the TCC is the same. Then this gives the set of time and current coordinates. Again, we are injecting different fusing currents, and the related operating time is noted down. This is done in multiple steps, and then the final TCC is given by the manufacturer.
So I'll just like to add here is that what we have tried to do is there's a lot of literature available, right, in over the internet, which will give you information about these protective devices. But our attempt has been to try and bring out concepts which are not very easily available, and which will allow, once again, as I mentioned earlier, to build a base to really doing or understanding a proper protective device coordination. Like the whole idea is that while we do protective device coordination, all of these elements of what we discussed, like till now, operating time, time current characteristics, and all, they play a big role. And hence, it becomes very important for someone who is actually reviewing a protection device study to be able to respect and to be able to, in a way, appreciate the nitty-gritties that we need to go while doing a proper PD study. So with that, I think we'll go to the next of accuracy and tolerances for fuses.
Yeah.
or any PDs for that.
Yeah, right. So then the IC, because each manufacturer will have a different kind of manufacturing process, and there is possibility of tolerances. Each and every fuse series may not have the same type of operating time. So IEC standard specifies the minimum requirements of each protecting devices. So manufacturer shall comply to all given minimum requirements of the standards. Now this opens up the another important topic, that is accuracy and the tolerances. Okay, so there are three types of accuracies specified as per the standards. One is intrinsic accuracy, the second is operating accuracy, and then there is a total system accuracy. So intrinsic is basically gives the uncertainty in the measuring of the sensing quantities or the energizing quantities. So we know that there is always error in the measurement. So that is allotted in a intrinsic accuracy. Then we know that there are certain influencing quantities there. And the one is temperature. Then there is a harmonics. Then there is a different environmental aspects, such as humidity, altitudes, that influence the total operating time of the system. So that variation and the intrinsic accuracy, this both comprising the operating accuracy. And then there is a total system accuracy. So the total effect of intrinsic and operating accuracy gives the total system accuracy. So here we might have different theoretical equations for operating time, but there is always it is always associated with these three accuracies. So for example, I'm trying to explain you what is intrinsic here. So suppose we have a fault of 2000 ampere and the protection device measure it as a 1996 ampere. So the 4 ampere is the accuracy level that is defined as a intrinsic accuracy, and that comes out to be 0.2 percentage. Then there is a second test that is to be carried out by the manufacturer, that here the condition is specified as per the standard. But now there is a variation that is bring into the temperature, that is ambient temperature. And again, the test is carried out. Then at this time, the protection device reads the fault current as a 1994 ampere. Again, there is a lesser quantity is measured. So this is basically 0.1% variation accuracy that is based on the this accuracy based on 1996 ampere. Then we are again using, let's say, a 0.5 class CT sensors, and then this will again add a 0.5 additional variation into the system. So the complete accuracy of the total accuracy of the system would be the intrinsic accuracy plus 1.15 times the square root of all the variations, that is because of operating. And then additional to this, the external factors such as CT, that variation that also we will have to add. So this is basically gives the complete total current characteristics of that particular protection devices. So it will not be a line always. It will always have plus minus, that is maximum and minimum specified. Okay, so this is common for all PDs.
I think this is very important to understand that whatever we are talking about is about applicable to most of the production devices. Be it a fuse, be it a breaker, be it a relay. This variation due to the accuracy will impact the tolerances that we are going to be subjecting these the entire coordination study. So hence it's important to understand why we need to have the tolerance. You might be seeing while you do a PDC that there is a plus or minus 10%, plus or minus 20% tolerance that we are doing in the TCC. That the reason for that to come is this. Okay.
So I'm just handing it over to Nikhil
Yeah, I mean, I guess marketing team will not allow us to speak only technical, and they'll require 2 minutes of your time to just tell what we do. Nikhil, not more than 120 seconds.
Thank you so much, Prasad sir and Rajan sir. So before we dive into much more technical discussions, let me quickly introduce Efficienergi Consulting to all of you. So, founded in 2014 with a vision of reshaping the way electrical networks are managed, Efficienergi is an award-winning independent consulting company specializing in improving reliability, efficiency of data center with complete MEP solutions from design stage till expansion stage, which include like L1 to L5 greenfield testing, commissioning, design validations, power system studies, risk management, audits, PU optimization, and much more. So our focus in today's context, which is power system studies, comes from our hands-on experience with more than 500 facilities, including over 800 megawatt of data center capacity, which we have validated. So Efficienergi has delivered comprehensive electrical design validations for greenfield and brownfield sites from ranging from 2 megawatt to 150 megawatt IT load. So here in Efficienergi, we have a team of more than 45 electrical and mechanical engineers with experience in data centers since the last 10 years in design validation, load flow, protective device coordinations, arc flag, harmonics, short circuit, etc. We are also working during the operational stages for more than 200 megawatt of data center capacity, where we focus on single point of failure analysis, reliability studies, risk management, and efficiency studies, which allows us a holistic view of what mistakes can be rectified during the greenfield stage itself. So whether it's designing for selectivity, evaluating arc flash risks, or optimizing relays to minimize the cascading failures, our goal is to make the electrical network more reliable, compliant, and future ready. So with that, let's dive into the much more technical topic. So I will drop our contact details in the Q&A. You guys, if you have any queries, you can connect with us. So over to you, Rajan sir and Prasad sir.
Thank you, Nikhil. That was quick and like we like it in the small buckets. So time for a small poll in between. I think before we dive into what is IN and IR, we would like to hear from you. What is the similarity between IN and IR? Are they both maximum continuous current? Are they both adjustable? Is it both of the above or is it none of the above? Be interesting to hear your perspectives, to read your perspectives, so that we can take that topic a little more in detail. So if you want to qualify a little bit IN and IR for people who do not know, Prasad, what is IN and what is IR in that context? You want to expand a little bit?
Okay, the poll is completed or?
No, but you can just mention about IN and IR, maybe a little bit.
Basically, IN, what we say it is a nominal current, and IR we say that say it as a rated current, so rated trip current, basically.
So we have about 35%, 40% participation.
Mixed results.
Okay, yeah, it's pretty evenly distributed. With
The question looks confusing.
confusing.
Yeah. So
You want to go ahead and break the suspense?
yeah, because the one who is voting for B, they might be saying a different frame size they can select. So for that perspective, B is also correct. And the A is obviously the right answer. So B is not a right answer because IN is always fixed. It cannot be adjustable. What we adjust is IR basically. So the similarity between them is only the IN can be IR, but it is not always true that IR can be IN. Okay, so we'll move to the next slide, and we have almost completed the fuse. We are planning for a dedicated topic on each particular protective device, starting from its construction, and the working principle that is also in our mind to have it. But here again, the LVCB will be talking about the trip units again. So then here we have two kind of trip units. One is thermal magnetic and the other one is electronic trip units. So this is basically the ABB thermal magnetic breaker trip curves that we have taken from the ABB manuals. So this is TMF, TMD, and there is one TMA, they call it at. Then this one is basically fixed time where you cannot adjust the overload, and again you cannot adjust the magnetic tripping as well. So this is particularly fixed kind of breakers. So these breakers is normally used directly for the protection of the short circuit region. Then there is another thermal magnetic unit where you can adjust the thermal trip units, but magnetic trip is again fixed. And there is a third one wherein you adjust the thermal trip as well as the magnetic trip. So these three kind of trip units that we can see in thermal magnetic. Again, this region particular is covering for the overload of the protection requirements. So this is particularly, as the name suggests, thermal, that is completely depends on the bimetallic characteristics of the element, tripping element that has been used in the breaker. Then this one is magnetic tripping. So magnetic tripping is completely based on the a magnetic plunger that picks up the energizing quantity, and generally it is in 10 to 20 milliseconds it trips. Then there is a third one where we only need a magnetic tripping, that only we need a short circuit protection, and overload protection is taken care by some overload relays. There we can use this kind of TCC curve. Again, these are a single line curves. This will add up the tolerances, and we can see the maximum and minimum in this TCC. Now I'm just moving to the next. So here we have mentioned that there is no specific Kerr equation. The coordinates are completely obtained by test. So every manufacturer has to do the test, and they have to bring this TCC after testing only. Okay, then we are moving to the LVCB, which is MCCB and the power circuit breakers. Normally we use air circuit breakers here. LVCB, the familiar terms are always LSIGN, the long time, short time, instantaneous, ground fault, and the neutral protection. So here you must have heard long time pickup, then a long time delay. So long time pickup, we call it as a IR, and time delay, we call it as a TR. In short time, we call it ISD, and for time delay, we say TSD. So again, it is a regular concept. It tips on the sustained overvolts and works on I square T. Here, this I will elaborate more. We'll move to the next slide. Okay. So there is a general curve equation, that is, we say it as a theoretical curve equation for electronic trip units. So that we basically know that I square, that is inversely proportional to the time. This gives this particular equation, I square T is equal to constant. Now, how does this equation is used to draw the curve? I'll be explaining you in the next slide, but here we know that IR, we basically have the settings starts from 0.4 and goes up to the 100% of the ions nominal current. And then we have a TR which usually starts from 0.5 seconds and go up to 24 seconds. Then in regular I square T, first of all, we have to obtain this K. So for this K to obtain, we need to know what is the I that we should be considering and what is the T that is there in a set value. So normally what we do, we take 6 times of the IR as the base for I. So let's say we have considered 1 as a IR, 1 into IN. So then that will be 6 into 1, that will be 6 square, and time, let's say we have considered 3 seconds as a tripping time. So what does basically it does mean? It means is when the current will go the 6 times of the set current, then the particular PD will trip on the TR. If we have set it as a 3 seconds, then it will trip in 3 seconds. When the current IR will go the 6 times of the IR settings, when the fault current will go 6 times of the IR. So once this K is calculated, we can have the operating time for each and every fault current that we are desired to know the operating time. So this K is fixed, and we can have different operating fault current, let's say 2 times, 3 times, and we can calculate this T. Again, this T will have the it is a theoretical value. Again, this will have a tolerances added to it. So if you see the curve of any protection device starts from 1.05 times of the set value. Suppose we are setting, let's say, a 4000 ampere breaker, we are setting it at 4000 ampere. It will never start at 4000 ampere. It will always start 4000 into 1.05 times. That comes around 4200 amperes. So because this is the requirement of IEC standard. So what IEC says, the any tripping current has to withstand to 1.05 times the set value. So the tripping should not occur below this value. I'll show you here in ETAB. I can show you. I have a ETAB window open for this. So here, if you see, this is ABB breaker. This is set at 4000 ampere. Here you can see it is set at 4000 ampere, but it will always start at 4200 ampere. So if this is the minimum line, if you see, it will be 4200 ampere. You can see this on the screen. It is 4200 ampere. That is 1.05 times of the set value. It is actually the requirement of the my screen is shared still, right? Okay. So we'll explain you how it is basically to be interpreted. So this is particularly the ABB EquipTouch TCC. Here this data is taken from the ABB manual. Here you can see for the long time they have given the threshold tolerances, and there is a tolerances in the time as well. So here you can see it is starting at 1.05 times. So that care we have to be, that has to be taken, because if you are saying 4000 is the limit that we have to start our operation time, then we cannot set it at a 4000 ampere. We have to set it lower than the 4000 ampere. Then only the purpose of the protection will be achieved. For this particular TCC, they have given this equation, which is 9 times the TR divided by fault current into the set current square. That is square of this. So if I see, you can see here we have the setting of IR is 1, TR is 4. So 9 into 4, and then we have, let's say we are measuring for 2 times of the current, that is 8000, 4000 into 2. So we'll be having fault current 2 times of the IR value. So 2 divided by 1, that 4 again. If you calculate, this is coming around to be 9 seconds. So theoretical value for 8000 ampere fault current, the operating time should be 9 seconds. But as we know, there is a tolerances of plus minus 20%. Here you can see they have given 10% as the tolerance. but there is also one suffix written over here, that is 3. So this 3 means these tolerances is again applied only if the conditions are specified as per standard. But on site, the specified conditions are not always there. So normally they take it plus minus 20%, irrespective of the conditions. And accordingly, this curve is made. So you can see 9 seconds. So 120% we do it 1.2 times of the 9. This is coming around 108, that is 10.8 seconds. And 0.8 times of 9 seconds, this will be come around 7.2 seconds. So that you can clearly see here. So that is where the minimum and maximum tolerances comes into the play when we have to coordinate the series breakers. It is also called as a minimum committed time. So the 7.2 is the minimum committed time, that for 8000 ampere, this particular protection device will not trip less than 7.2 seconds. So that is a committed time. So the next one we have again the same thing applies to the short time region also. Short time we also have the definite time features. So there we can have a fixed time irrespective of the current magnitude. So it is not there is no any relationship of inverse proportionality. This is basically done or required for the coordination purpose for the selectivity. Then we have the instantaneous and overrides. So instantaneous, as the name suggests, it is instantaneous. So once the pickup is achieved, the current level at which the tripping function picks up, then tripping is initiated immediately with no intentional delay. Then there is an override feature available in the breaker. That is basically to protect the breaker itself, because when we set a short time pickup, we in some breakers we can disable the instantaneous. So those breakers are a class B classified as per the IC. That means it can withstand to, let's say, 0.5 seconds up to the breaking capacity of the breaker. But some of the breakers it is not possible. So there they give the override function in the breaker. I will explain this particularly in the short circuit withstand duty of the breakers. Okay, next again we'll be shifting to relays, but for that there is a poll.
So there are two types of, I mean, general nomenclature wise, people talk about a digital or a numeric relay. So what do you think? What's your opinion on that? So just to sum up till then, we have covered, I think, fuses and breakers, both very important elements of protection schema in various mission critical facilities. So hope that allowed you to get a little more broader understanding and a deeper understanding of why selection, I mean, what manner you need to select different elements. Especially it becomes very important when you have multiple different types of makes in a single facility. You have different types like electronic trip units, you have thermal magnetic and so on. So the more you know about the ways in which the operating characteristics of these protection devices occurs, it will allow a better coordination study to be done, to appreciate the differences and decide what are the limitations, so that at the design stage itself, some of these things can be, taken care of. So let's see if we have our poll results coming in. There is a bias towards a certain option. Let's see whether that is correct. So we almost more than 50% people have answered. So maybe we can go ahead with the result. Prasad, over to you
Okay.
to break the suspense. The C is what people feel. Digital relay is more advanced than numerical.
Okay. So basically, that is not true. So digital relay is not advanced. Actually, the numerical relays are more advanced than the digital relays, because in digital relays, the digital relays uses the binary input plus minus and 1 and 0. But in numerical relays, the numerical relays can take up the sensing quantities directly and can work on the logic and give the faster result than the digital relays. So that is not the answer for this. Both are same. In some part they are same, but they are not same in totality. Uses similar signal processing? No, they are not using similar signal processing. One works on the digital inputs. A numerical can take the analog inputs directly and can convert it to the desired output. So the answer is actually none of the above. Okay, again, this is the constructional aspects of the relay that we are not going to talk about today. We are going to talk about the tripping characteristics of the relay. So we all know that relay, basically we always hear this IDMT and DT. So IDMT, we say inverse definite minimum time curves, and there is a definite time curves. Here we can, we always see this tags that is given by NC standards 50 and 51. But now, as we are using the communication protocol as per IC 61850, then it has a logic nodes which is denoted by PIOC and TIOC. IOC means here written here instantaneous overcurrent, and TOC means time overcurrent. So time overcurrent and instantaneous overcurrent. Again, there are different terms used by the different standards. INC will be using a different terms, and IC will be using the different terms. But the meaning of the both are same. So what is basically 50-51? So in a standard term, 51 is independent time characteristics, because it depends on the operating time depends on the quantity of the current, and then 50 is it is called as a dependent time characteristics. So this is basically actually it is reversed. Independent time characteristics is instantaneous, and dependent time characteristics is 51, whereas we have the equations given by the IC. Okay, so IC relay equations as per IC 60255 that is specifically for the overcurrent relays, and the time of operation is given by the TDS, or what we call it as a so T is the time of operation, that is TDS, that is time dial setting. We sometimes we use TMS also, time multiplier settings. Then there is a constant term K. Then this is a fault current, and this is the pickup current, set value of the current, and this is the time required to be means the current for which we are calculating the time. Then there is a power of alpha -1 plus C. So K, alpha, and C are defined by the IEC for different inversities. Inversities means extremely inverse. Then we have very inverse. Then we have a standard inverse. So for these three inversity, the value will vary, and we can have different characteristics of the tripping. Again, in today's, as I said, in numerical relays, basically, we can feed this value, and we can create our own curve as well, as per the requirement of the protection. So it is not always required that you go for extremely inverse or very inverse. There are advanced relays wherein we can have our own relay equations. Again, for this equation is given by IEC, and IEC, what does they require is the dependent time characteristics should be complying in this range, 2 times of the set value up to the 20 times of the set value. So in some of the relays you must have seen after the 20 there is a definite time characteristics, then it doesn't follow any equations. So that is not the limitations of the relay. It is basically the requirements of the standards, and every manufacturer try to follow these requirements. Again, there are certain relays where you can see this value can be even go up to the 40 times. So that depends on the manufacturer and its manufacturing process. But as per standard, this is the basic requirement. So most of the relays you will find working in this region only. After 20 times, we cannot actually follow this equation. So this particular case will come across, will be a difficult when there is a coordination required after 20 times of the set current. When the fault current is very high, which is going more than 20 of the set value. That again, this is the one challenge that we'll be covering in our coordination webinar. Okay, now let's see one calculation for operating time of the relay with extremely inverse curve.
So I'll just interject here, Prasad, just to expand on the audience's knowledge. If you can quickly just talk about the different curves, standard, extremely inverse, normal inverse, what do they denote, and maybe explain it with an example.
Yeah, right. So here, basically you can see these two curves. These two curves have been set to the same values. So pickup is same, the TDS is same, the time dial setting is same, everything is same. But one is with the extremely inverse characteristics and one is with the standard characteristics. So you can see for a 290 ampere, one is tripping faster than the other. So standard inverse, you can see it is tripping at a lower magnitude of time, that is 10.2 seconds, whereas the extremely inverse is tripping at 21.5 seconds. So this nature of this curve can be used where we are protecting equipment which is having a high inrush currents or which is having a high starting or a short time maximum. So for that, let's say we have a transformer. So normally you must have seen the transformer. We generally go for extremely inverse characteristics. The reason being the transformer is having high inrush current. So and again the transformer has to carry the full load of the system. There is a possibility that for a shorter period of time there is a huge requirement of the load. A cold loading also can be higher in this stage. So for that we don't want to trip the system at a faster time. So we want a delayed time. So here you can see the time is delayed for the same magnitude. So this is extremely inverse. So inversity in this region is very extreme. Here also you can see the difference. So now as you move on to the higher and higher magnitude, the time for this will increase. So this is a break point. So here the extreme inverse curve will take over and it will trip faster than the standard. In this region, the standard curve will trip faster than the extremely inverse. So these both characteristics is used while we are protecting a particular equipment. So for transformer, it is this we will use, and for the feeder protection, we will use standard inverse. Because feeder of we want a delayed time for a higher magnitude. So here with the example of this equation that is given as per the IEC, we are just trying to calculate So for extremely inverse, the value for this constant k is 80, c is 0, and alpha is 2. Again, with the same curve, we are considering 290. We just want to find out what is the tripping time for a 290 ampere. And we are setting this curve, the set value is 120. So the fault current is 290 and the set value is 120. And if we calculate, it is for this, alpha is this, and C is this. So if you calculate this, it is coming around 21.2 seconds. So here you can see for extremely inverse, we are getting on the TCC 21.5 seconds. Again, these are only the curves equation. As I said, we can also customize it by having different value of K, C, and alpha. Then this is based on IC standard. Then ANSI standard is having its own equation and the constants.
So I think we'll have to probably take up CTI a bit faster because we're already running out of time.
Yeah.
I guess then we'll have to keep some time for Q&A.
Okay. So again, this is again the theoretical values because here you will see there is no maximum minimum specified in this eta because the relay is only gives the tripping signal. The tripping has to be carried out by the auxiliary relays and the circuit breakers. And there is no fixed combination of a relay or a circuit breaker. If there is a fixed combination, then we can define maximum minimum. But relays can be used with any combination of auxiliary relays as well as the breakers. So here we only get this kind of curves. Now it is the understanding of the coordination engineer to use this time with the proper tolerances, and that is where the coordination time interval comes into the picture. So here, as I said, the relay TCC excludes the breaker opening time. Coordination requires additional time buffer, that is what we call a CTI. So coordination time interval ensures the selective tripping. Yeah, now what makes up the coordination time interval, CTI? So
yeah, I think this should be, we have already given a lot of hints till now. So maybe this question we should get the highest number of correct answers. And I think this is one of the most, I would say, significant or consequential concepts in a protection device coordination study. I mean, the name itself tells that. But most of the times, whenever we have debates, especially with utilities, and to allow us, we always fight. भैया थोड़ा CTI दे दो, थोड़ा हमको टाइम दे दो, कोऑर्डिनेशन करने के लिए जगह नहीं है. That is a bane that we always face, and which is why I think a deep dive into understanding what is CTI, what does IEEE 242 talk about, and all is what we'll take up in the next few slides. We are extending a little bit beyond our designated time slot. We hope you don't mind. We have had a very high amount of engagement. Almost no one is left, which tells us that probably you are, at least liking the session there so far. Let's see the poll and then continue further. Oh, okay. So yeah, as expected, people have given the right answer. Almost 70% of the team has answered right. It is all of the above.
Yeah, right. So basically, the CTI is why we require, as I explained you, we only know the operating time of the relay. We are not having the knowledge about the tolerances of the sensing equipment. We don't have the time for exact time of the breaker opening time that we don't have. Then we don't exactly have the same characteristic of the upstream relay. In downstream, you might be having a Siemens relay, but upstream you might be having a ABB relay. So again, the characteristics of those two relays in terms of tolerances might be different. So we don't have that knowledge. Then we don't have the knowledge of the overreach transient overreach of the each relay. CMS might have a different transient overreach. Then ABP will have a different transient overreach. Then we don't have the knowledge of resetting time, which is also called as a over travel time, or normally we say in standard terms it is a overshoot time. So that time tolerances we don't have. So normally, as per IEEE 242, which specifies the time coordination time interval required is in the range of 200 to 250 milliseconds. So earlier, the technology was not that advanced. So 200 to 50 milliseconds might be higher considering today's time. But again, that is the safest time because we are dealing with the MV side protections. So okay, so here it is given here. It is the sum of CP opening time, relay over travel, relay tolerances, and setting errors. So normally, what we see in today, there is a very little margin that we get, and the system is comprising of very higher sub levels. So up to the utility breaker, we have 3 to 4 stages in between, and we have to coordinate all these 3-4 stages. So considering 200 milliseconds for one stage, it comes around to be 800 or almost 1,000 seconds time, which is not 1,000 milliseconds time. So that which is impossible to coordinate with the utility breakers. So to have the knowledge of these three is much more important. We have seen some of the people might be thinking that just adding up the breaker opening time, whether will be solving the CPI issues, but the answer is no. We also have to see the relay over travel relay tolerances. So relay tolerances and setting errors that you must be having idea because we already said explained you this is the relay over travels. That overshoot means suppose what happens in the downstream, if suppose the fault current crosses the set value, now the relay goes into the operating state. So now it is operating time has been started. The counting has started. Okay, now it has to be tripped, let's say on 200 millisecond. But 200 millisecond before that, let's say maybe at 100 or 150 second, fault is cleared somehow. But still, this relay will pick up. So whatever time extra is required for this relay, that is basically overshoot time. So it is there with every relay. So that even if the breaker is downstream breaker or downstream system is isolating the fault, it is possibility that the upstream breaker will trip or due to it is not because it is not getting the proper resetting time. So that is possible. So we have to consider the relay over travel time as well. Again, the relay tolerances. So if you go deeper into the manufacturer's data sheet, you will always see there is a plus minus tolerances on the curve. But in ETAP study, you will never see minimum maximum given on the curves. It is always a theoretical value. But that plus minus 5% also we have to consider. We'll go more deeper into this when we'll be having the session on how to coordinate between the relays. So this is taken from 242 standard. So when we have here, you can see when we are working with the low voltage circuit breaker, it is just saying that clear space is required. So that we know because it is a banded curve, so the tolerances and everything is covered. So minimum maximum is explained by the curve itself. So our duty is only to have a small clear space between the two breakers. But in relays, basically here you can see the time, you can see 220 millisecond, 300 millisecond, 300. This for electromechanical. When we are dealing with the static relay, you can see 120 up to 200 milliseconds is required. So that has to be taken care of. But if you have enough data available wherein you are specifying all the tolerances, then we can have a different CTI as well. So summary, today's I think we have tried to cover the most which we can. There are a lot of questions maybe there, but that will be taking it in a Q&A. So key principle of fuses LVCB relays that we have gone through, the importance and how the melting time and arcing time, trip settings, selectivity that we have seen. And then the role of CTI. The role of CTI, I've just basically touched the topic of CTI. What is the importance of CTI in selectivity, in terms of selectivity, that yet to cover, that we'll be covering in a selectivity session.
So yeah, I think we've set a foundation. We will appreciate any questions that you want to ask. We have a question that has come in. Can we minimize the inrush tripping, and what will be the technical reasons of inrush? So Prasad, you want to take that?
Okay, 1 second.
Is it possible to minimize inrush first of all?
Yeah, inrush can be minimized. Definitely, because if you see the basic of the inrush, the basic equation, then there, if you start at the voltage peak of the supply, then you will have a minimum inrush, because the magnetic flux always lags 90 degrees behind the voltage. So in that case, I think a Hitachi or Alstom, they are having a different kind of breakers which closes on the zero crossing of the peak. That is peak crossing basically. So that can be done. Okay, any other questions?
Mr. Weber, if you have a question, please drop it in Q&A.
Yeah, we can. I think we can allow him to talk. Mr. Weber, you've been allowed to talk if you want to speak. Please feel free. You have been unmuted. You can unmute yourself and speak. Hello, Mr. Weber, can you hear us?
Hello.
Yes, please go ahead if you have any questions.
Hello. Actually, I have one question. Like, we're having a GIS where we taken the LTS scheme. I'm working in the GIS earlier before also, but number of GIS are working. I've never introduced about the LTS scheme, but right now in the Mumbai region, in the Navi Mumbai regions, the government was introducing the LTS scheme. I don't know much about that scheme. Can you having the idea about that scheme, or can you lighting up something about that?
No, LTS, I've not heard of it. Like, what is exactly LTS?
Basically, it's load trimming scheme.
Trailing.
Load trimming.
Train, you are saying trailing, or what you saying?
Load trimming scheme.
Oh no, I have not heard of this scheme, because I don't have, I've not gone through this.
Yeah, anything related to coordination, related to CTI, related to operating times, characteristics, curves, anything that can be put in Q&A. Vaibhavji, if there's something else, we can take that up. We have one more hand raised. Okay, Vivek ji, just a minute. Yeah, we can unmute him. Okay. Vivek, you can please speak. Vivek, you'll be able to speak now.
Yeah. Team, I am audible?
Yes, yes.
Yeah. So one my question. So I have a two breaker on HT upstream. Okay. So up downstream breaker we have a setting of 51 and 50. Okay. That instant this or time dated, and one is definite time 50. Okay. And upstream is the same 50 and 51 and 50 protection. And the coordination, this we have given this 50 by grading of time CTI by 200 millisecond between the up breakers. Okay, so so can we this that once my this fault current, that is suppose 50 is the set, we have a setting of 0.35. Okay, 300 millisecond, and upstream we have setting of this zero point 0.5 200 time interval. And this instant this 51, suppose if there is a fault happen and it crosses the threshold value of 50 downstream, and simultaneously this upstream 51 also that setting generated that will also activate, so both the breaker will trip.
No, I'm not getting your question, but because you are saying at downstream you are setting it as a at a 300 milliseconds, and upstream you are setting it at a 500.
500, so okay, 500, but the current that is fault current, that is not crossing the threshold value of upstream 50, but it is
Okay.
crossing the downstream 50. Okay, but
Okay.
but the
But if the
upstream
CPI is
51
not,
timing is coming less than your downstream 50. So which breaker will trip, upstream or downstream?
but then it is miscoordinated, na? If the curve is coming down and that is left to the downstream breaker, then this is miscoordination.
Okay, this is a miscoordination.
Because the curve will be visible, na? If it is tripping at a lesser time than the downstream breaker. It is visible, it must be visible in the ETA file or the coordination curve.
Okay. Because this report it is showing, that's why it's because this same it is observation I have put it. Okay, thank you.
Yeah, you can please share that
Yeah,
over
TCC.
email, the TCC, and we can take this up further. Nikhil, you can put the email addresses in the chat. Okay, we have one more person who wants to say something. Mr. Anand, you can please unmute and speak. Mr. Anand, you can unmute and speak here, right now if you have any questions.
Am I audible now?
Yes, yes.
My question is that suppose from one of the substation there are multiple outgoing feeders, right? One it has 500 meter, one it has 700 meter, and if voltage fluctuation happens, then there will be a difference in magnitude for both locations, or magnitude of voltage drop is the same.
A voltage fluctuation, if it is occurring from the source side, then you will be seeing again the difference depends on how much load is there at the time of fluctuation.
Okay, suppose we consider the same load from both location, but distance is different.
Yeah, then this is the longer the cable is, the higher the drop will be.
Okay, means time will be same and dropping percentage will be the more, right?
Yeah, yes.
Okay, thanks.
I think Vaibhavji, you want to speak? You can speak. In case you, I think you raised a hand again.
Actually, I have one more doubt. In the data centers, we're having the RMU systems. So in the RMU systems, basically, we having the relay coordination. So sometimes I observe that okay, in the RMUs, we kept the equal means the same relay coordination on the ring mean in the terms of ring panels. But what will be the suggested relay coordination we have to put in the RMU systems, ring system basically for the ring?
Okay, see here basically now the RMU, the concept of RMU, what I understand is basically when we have two sources feeding to the load parallelly. Okay, so
Yes.
that case is basically works for RMU. But now we are having RMU. Let's say in data center, we are having it just for the case of reliability. Okay. Again, as I said, the coordination time interval is important. So if you are not, if you have a 3 to 4 RMUs in between the incomer and the feeder, so it is not possible to maintain the CTI. But this problem is to be solved by reverse blocking feature of the relay. That is the only solution.
We can put reverse blocking to each relay. So we have to get the communication from end to end, na?
No, not required. You need to have only communication between the RMU incomer, the RMU ring incomer, and the RMU ties.
Okay. So the relay coordination will be. My question is I've simplified the question for year end. Maybe from the starting ring and the ending ring. Means we have the two sources. So for the two incomers, the relay setting will be higher side, and for the middle of the RMU, it will be lower side. It will be corrected, or it will be same for the all RMUs in the ring.
No, incomer must have the higher settings, and
Okay.
the tiebreakers you can have the same settings. See, ultimately, the requirement is how much portion of your power system is protected when there is a fault.
Right.
So, in some cases, if suppose I don't have a high CTI from the utility, then that time I will see which RMU line that I have to. There will be no problem if one RMU line trips. Complete RMU. So you might be having a different RMU line for IT. You might be having a different lineup for cooling system, right? So what is important for you that you have to consider, and accordingly you have to see where you can compromise on. So this is
No,
coordination, basically the compromises that we have to make.
we cannot compromise any line because it's not about the IT lineup line or non-IT. It's a mix of the all combinations. We consider the IT, non-IT, and the house load in the one rings.
Okay.
So basically, so we cannot compromise one line. But yes, is there anything else we can put the means as you said that the blocking relay blocking? How can
Yeah.
we put that relay blocking to end? Is there any if any malfunction or miscommunication between the relays, so it
No,
can trip the my upstream breaker also, right?
no, here in case if it is not properly coordinated, as you are saying that you are keeping the same settings for all the RMUs, then there is a chance of malfunction or tripping or cascading. But in reverse blocking, it is not a.
So for the reverse blocking, it will be two-sided of source. So it will be blocking the incoming and outgoing also, right? Right.
Yeah, let it be a two-sided source. We can have a directional protection added in the feature in the reverse blocking feature. So that option is also there. It can read the direction and then can block the relays.
Right. So the means the fault of relay will be isolated, right?
Yes. That
Okay.
previous working we already have given in many places. Uh, that implementation part, that is you have to take care of. We can give you that is very general scheme. It is not very high tech scheme.
Okay. Thank you.
In detail, yeah, Vaibhav, if you require, you can message across or mail across. We can discuss in more detail.
Thank you.
Yeah, and we'll request if you can fill up the feedback. That will really help us to fine tune and curate our content for the next series of this webinar. So as we said, this was just a very basic initial basic precursor, a teaser you can say, for opening up this whole topic of protective device coordination as well as power system studies. We would like to have this as a long running series to add more value. We really appreciate all of you to fill out the Google form and provide your valuable feedback for us to curate the content later on. And anything else, if you have any more queries and questions, please feel free to drop a mail or call up directly on the Nikhil's number. He will be happy to assist you. With this, I think I would like to thank Prasad and my colleagues for sharing the knowledge, and all of you most importantly for attending, giving us your time. It was a very healthy attendance that we had. Thank you so much. We just hope it did add some value and some more understanding to your already rich experience that each of you probably bring to the table, and look forward to continuing this even further. Yeah, thank you everyone. With this, we'll end this session. Thank you so much.
Thanks. Thank you so much, everyone. So,
Your phone to a paired on the